All right, well, let's go ahead and get started. So my name is Jeremy Siek. It's my pleasure to be here at LambdaConf and looking forward to this morning. It's a little bit of background. I'm a professor at Indiana University. I've been doing research in programming languages for a long time now, since about 2000 timeframe. It's good to be back in Boulder. I used to be a professor at University of Colorado in Boulder. And then about 4 years I was lured away back to Indiana University, which is a hotbed of functional programming. That's one of the main reasons that drew me back to Bloomington. And as you walk around, I know there's a number of volunteers from Indiana University, and so you'll definitely see other people from IU. So that's what drew me back to Bloomington. I did my PhD there as well. So over the years I've sort of made a transition to functional programming. I started out as a C++ programmer, doing code for doing high-performance linear algebra, sort of like matrix computations, and then I got into graph computations, as in like nodes and edges, and was involved with the Boost group, so I very much into open source development. But then thanks to being at Indiana University, I was exposed to Scheme and Racket and all these functional programming languages. Ended up, my PhD thesis software was all written in OCaml. I was just telling my colleague Dana that I had, about a month into the project, I'd been writing the code in C++ and spent all weekend debugging a memory error, and then got fed up and threw the whole thing in the trash can and started over in OCaml and never looked back. So, and never had another memory error to debug. So that was awesome. All right. So one of the things I've enjoyed doing over the years is blogging, and oftentimes I'm, writing about programming language research and whatever sort of strikes my fancy at the moment. And it's a lot of fun for when I get feedback from my friends reading the blog posts, some friends in industry, at one point it occurred to me that some of my friends really just couldn't read my blog posts at all because of the notation. It's all this funny Greek letters and weird symbols and horizontal lines, and what on earth does all that mean? Okay, so then a few years back I had this idea of, I'll write a blog post that tries to, as succinctly as I can, get the main ideas that's behind these funky notations. And so that blog post was really well received. And by far the most read of my blog posts by several orders of magnitude. And so I thought I'd go ahead and do it in person. And so this is my first time doing that blog post in person. I've changed the examples a little bit, but it still follows along quite closely. So if later on you want to go back and review what we did, you can just go ahead and check out the blog post. But definitely use this time as an interactive kind of thing where ask questions. I'm going to start out pretty sort of from the basics. Okay, so let's take a look at the sort of outline here. This first bullet here, a whole bunch of that hopefully is going to be just review of some really basic sort of simple math ideas. But definitely, if there's anything that doesn't quite make sense, definitely just stop me, put up your hand, ask a question, we'll get through that. Towards the end of that first section, there's going to be the super key idea that we talk about how do you define an infinite set. And then we're going to use that 3 times. We're going to use it over and over again in the next 3 sections. Okay, we're going to learn about the syntax we use for defining language syntax. Okay, so how do you define what syntactically is in your language? How we do that in programming language theory papers. We're going to cover that. We're going to talk about what's the operational semantics, which is how do you define what happens when you run a program. Let's say you're designing your own new language and you want to decide what happens when this particular construct is executed. That's what operational semantics does. And then finally, type systems. Let's say you're designing a type checker that's going to decide what programs get accepted by your type checker and what programs get rejected, and what kind of guarantees you might want out of your type system. We're going to talk about that in that last bullet, and something that's not even in that particular blog post, but a different blog post. We're going to do, if we have time, a quick proof of type safety for a little language. Okay, so we'll see if we can get that far. So it's a little bonus material. All right, so that's the plan. All right, so just really basic on sets. I think as a functional programmer, I think a lot more about lists than sets. And they're a little bit funky compared to lists, so it's worth spending a moment on them. What is a set? It's just a collection of objects. That 0 with a slash through it's the empty set. It has nothing in it. There's another set over there that has 0, 1, and 2 in it. Order doesn't matter. Duplication doesn't matter. All of those sets there that I've listed are really just the same thing. Okay? The fact that I change the order doesn't matter. That I put in multiple ones in the set to the right, that totally doesn't matter. They are the same set. There's all kinds of set operations like membership. So that funny E-like symbol there means in. That 1 is in the set and 3 is not in the set. And membership is sort of the only thing that matters from a set perspective. Like, really, you can define equality of a set. Like, two sets are equal when the same things are in them. Okay. We've got union there. You can take the union of two sets, and you get a new set that has everything from both sets. You know, intersection. You get the things that were. You get only the things that were in both, whereas the other you get, for a union, you get stuff that's in either of them, right? Set difference there. You take everything from that second set out of the first set, right? So you're just left with 0. Doesn't matter. That 3 doesn't matter, okay? Now so all of these sets up above are all finite sets. They just had a fixed number of elements in them. And from a programming perspective, it's easy for me to think about those. But oftentimes in math, we start talking about infinite sets. And here's some really familiar ones, like the natural numbers, 0, 1, 2. You know, the integers has all the negatives in there as well. Okay, so, and we're going to spend a lot of time talking about infinite sets today, okay, because lots of things in programming languages end up being infinite sets, okay. So those little ellipses there, those little dots, I always find them kind of troubling and worrying if people are trying to define their sets with ... right? It just means and so on. Well, what does that really mean? So we're gonna talk about a way to be more precise and not have to use the ... Okay. So I'm also, one thing about this, I'm going to have some questions that I give you throughout. We're going to take little pauses, maybe like 2, 3, 5-minute pauses here and there, and I'll ask you to whip out your laptop, your paper and pencil, and answer some little questions. But just as a warm-up, here's a little question for y'all. Don't need paper for this one, but just if x and y are sets, if x is equal to the union of the set with 0 and y, is it true that 0 is not in y? Yeah, not necessarily. Yeah, it's a little bit of a trick question there, but you don't know. Because why, right? Because 0, you know, when you union two things, 0 might have already been in y, and then it'll also be in the union, or it might not have been, and then it'll be in the union. So we definitely know that 0 is in x afterwards, but we don't know anything about whether 0 is in y. And that's something that has caught me up, years past when playing around with sets and thinking about them. All right, tuples, right? So here order matters, right? So you've got a sequence of objects. If it's just 2 objects, we call it a pair, right? So there's some examples of tuples. Some people like the round parentheses. Some people like the angle brackets. I flip-flop personally. So if I flip-flop, please forgive me. Order and duplication matters. Okay, so the 0, 1, 2 and the 2, 0, 1, those are different tuples. 0, 0 or 0, 0, 1 and 0, 1, those are different tuples, and so on. Okay, you can use these subscripts down at the bottom there to index and sort of do, access the nth element, kind of like you were accessing into an array or something. And I always go 0 indexed because I'm a computer scientist, but some people do one indexed. All right, a lot of what we're going to be talking about today are relations. Okay, relations, it's just a set of pairs, and they're usually representing some kind of association. Okay, right, so maybe maybe Anne, is associated with Jane, and Mary Jane, Mary associated with Jane. That has me thinking of skiing. There's a really great ski area nearby called Mary Jane. Awesome, moguls, so much fun. All right, so relation, just a set of pairs. And they can be infinite too, right? A function, it's just a special kind of relation. But now for every, thing on the left, we're only going to associate it with one thing on the right, okay? So, and then we've got this new notation where, if 0 goes to 1, then we can say f of 0 equals 1, right, using that functional notation, okay? And just like sets, functions can be infinite, right? You can have, again, I've got these ... dots going along, right, for this increment function. And again, that ... should be kind of troubling. Okay, let's see here. All right, so just a quick pause there. Any questions so far, comments, hopefully?
So the notation for functions and the notation for sets overlap, like they're both equally braces.
Yes, because a function is a set.
Okay.
It literally is a set. Some sets have dogs in them, some sets have pairs in them. If they have pairs in them, then it's a relation. And then furthermore, if it has this, everything on the left is only associated with one thing on the right, then not only is it a set, not only is it relation, but it's also a function. So there's like these criteria that keep getting added on.
Do we consider these functions to be total functions?
I'm
saying at most one other entity, and I'm thinking partial total.
Yeah, so like what you're asking about is like, what if I deleted this line coming out of 3 and I didn't send 3 anywhere? That would be a partial function. We're going to be talking about total functions today. Actually, you know what? We're going to be mostly talking about relations, to tell you the truth. So we're not going to worry about it too much.
So f is a total function
over the 0 through 3 here, if that was your domain. Yeah, so yeah, normally if you want to be more sort of formal about this, whenever you talk about a function, you're supposed to specify its domain, the set that you're pulling your inputs out of, and then you can talk about whether you've covered all of your inputs or whether you forgot some of your inputs, or whether maybe on some inputs, if you're thinking programming, you might have divergence, and then it's sort of undefined and all that jazz. Yeah, but we're not going to have to worry too much about that today. But that's a good question. Yeah, I'm somewhat glossing over a few kind of things here, trying to keep sort of focus on some of the main ideas. But those are happy to take questions like that. Yeah. Okay. All right. Okay, this is where you may not have seen this before. How do you define an infinite set in a completely precise manner? Okay, I like to call this definition by rules. That's not a standard terminology. I pulled that out of my you-know-what. But it says what it is. The fancy name is inductively defined set. Okay? The idea here is that we're going to write down a collection of rules that says what's in the set. Okay? Now, these rules usually have one of two forms. A lot of the rules are going to be if-then kind of rules. It says that if this thing is in the set, then this other thing is also in the set. And usually it's like if this little thing is in the set, then this slightly bigger thing is in the set. Okay? There's also, that's like that second rule there is an example of that. The first rule there is the other kind of rule, which oftentimes I think of as like an axiom or something, but there's no if-then. It just says directly this thing is in there. Okay? So we have these rules, and then the idea is that all the things that you can sort of justify by the rules as being in the set are in there. Right? So if you can sort of follow the rules and show that something's in the set using those rules, then indeed it's in there. And if you can't do that, if there's, you might wonder, like, is is 5, 10 in the set, in the increment set. And can you follow these rules to justify 5, 10? No, you can't. Okay, so the things that you can't justify, they're not there. Okay, so only the things that are justified by the rules. Okay. You might find it a little bit unsettling that we're being recursive here, in the sense that our if-then statement is talking about the set that we're trying to define in the premise and in the conclusion, not just in the conclusion. So it's this recursive thing going on, and that's okay. All right. Okay.
Yeah, so like you suddenly introduce this like idea about building infinite sets.
Yeah.
But probably for like strictness, it makes sense to say, what does it mean, an infinite set?
Well, so I mean, maybe you're hinting at some things I'm about to get to, but you can write down collection of rules that don't define sets and that are garbage. And all I'm going to do is go over a couple rules of thumb about that in a second, but I'm not going to get into the theory behind that. I mean, we could start to talk about fixed points and monotone operators and all these wonderful things, and I'll give some pointers in the reading list about that. But I don't want to. But for someone that's just trying to read some papers about programming language theory, we don't have to go all that far into it. And so I'm going to spend time on other things. Yep.
Can you turn those inductively defined rules through some transformation into a set, or into a set of rules that will allow you to determine whether something is or is not? You said earlier that like 5, 10 isn't in the set. And I think a lot of people can intuit why that's true, but I don't do the rules of whether or not something is in the set directly follow from the inductive rules?
That's a good question. Oftentimes when you're trying to show that something doesn't appear in the set, you have to sort of do you have to do case analysis on all the rules. And if you can sort of exhaustively go through all the rules with your sort of thing in mind and show that it couldn't possibly work for each of the rules, then you're good to go. Sometimes you have to do an inductive proof, and we're going to talk about that later, that you might need for that. I think the way I've defined it here, for this particular relation, you might need an inductive proof to show that 5 and 10 is not there. So, yep.
What do you use an inductive proof even more to say if anything belongs, then the second is just one more than the first.
Yeah.
I mean, from these rules, you inductively prove that.
That's right. You could.
Something that holds for all the elements.
That's right. And then from that property, you could then easily show that 5, 10 is not in there. That's right. Yep. All right. All right, so let's talk about nonsensical rules. So I've got 2 different sets of rules here. So just that 1, 2 is one collection. And you think about, well, am I defining a set R here? Well, no, I'm being contradictory, right? I'm like, okay, 0, 1 is in the set. Oh, wait, no, it's not in the set, all right? So this is just garbage. This is not a definition of a inductively defined set. This is just a garbage collection of rules, okay? What's wrong with that AB collection of rules? Yeah.
Doesn't have a base case?
Yeah, there's no base case. You've got 2 if-thens, and you're saying, well, if there's something in there, then there's this other thing in there, but we have no way to get started. And so now this time, the second collection of rules it's not quite as bad as the first collection. So the second set of rules, in some sense, does define a set. It's the empty set. And so it's like a very long-winded way of saying empty set. But I would still say that you really don't want to write a collection of rules like that either.
So you probably want to tell me just to stop talking. But so it seems like a lot of the time the rules technically define like an infinite family of sets, which are the things you can make through the rules plus a bunch of other stuff, right? And so you're doing something like take the smallest set, which follows all these rules.
Yeah. So.
And that tells us that this has to be.
Yeah. So remember I said I'm saying only those members justified by the rules and no more.
Okay.
So this is technically what's called the least fixed point of these rules. You can take greatest fixed points and things like that. So, and get other sets. Yeah.
I think people are usually saying intersections intersection of all the sets to satisfy those two.
That would give you the least, yeah.
Yeah.
That's
well,
right.
But, I mean, that's, but when people give an inductive definition like that, they say, I'm not thinking of anything other than what's specified by the rule.
Right. Yep.
Um,
And by the way, it's good that we're hanging out on these slides because this is like sort of like the most important thing today is
I've never seen like an inductively defined set that uses a negative rule that says like this is not in a set.
Yeah.
Or, if this is not in a set, then this is not in a set. If this is in a set, then this is not in a set.
Yeah.
I feel like there are probably good reasons to
Yeah.
avoid using not in.
Yeah.
in inductive
I mean, you get
definition. Like what.
and the technical thing is that you typically end up with what's called it's not monotonic anymore, and that's a condition that you need for getting a well-defined, inductively defined set. So, and the pointers I give at the end can give you more background about that thing. And so, for now, I just want to say, avoid using negation in these rules. You can get a long way without using negation. Include at least one non-recursive rule, if-then recursive rule. And if you follow those rules of thumb, you're going to be in pretty good shape most of the time. And if you do need to use negation for some reason, then you should go and read a whole lot more to find out exactly what the conditions are. Okay. All right, so maybe one of the burning questions in your mind was, what on earth are those horizontal lines all about that I've seen in POPL papers or ICFP papers? It's just a notation for if-then, okay? And maybe a little bit of for all thrown in, okay? So here's again our definition of inc with those two rules, rule number 1 and rule number 2, that says 0, 1 is an inc. For any n and m, if n and m is an inc, then n plus 1 and m plus 1 is there. This is what it looks like if we do that same definition just using the horizontal lines. Okay, so we put the premises on top and the conclusion on the bottom. For rule number 1, there are no premises, so it just has a conclusion there. That's fine. For the second rule, the premise is you've got nm in inc, and if that's true, then n plus 1 and n plus 1 is in inc. Okay, yes?
Is there any sane interpretation if the bottom is blank but the top isn't?
No.
Okay,
Yeah.
So it's effectively, it's the proposition arrow, but just a line?
Yeah. Just implication, but.
I almost wore my POPL t-shirt today.
Oh!
And there's an imply.
Oh, good. Yeah. Now, one thing, so that's the basic idea. Now, one thing that's a little funny is when you're looking at the variable, like the n's and m's down there, right? They're placeholders for anything, right? And up in the rule, it said for any nm, right? It was very explicit that they were quantified as a for all, okay? When we go to the horizontal lines, we always leave out that quantification, okay? The for all quantification. So you have to sort of put that in your own mind again. That whenever you see any variables here, there's really this implicit for all or for out in front.
Is there a semantic value to the for the left-hand version? Like, would we be communicating something special by leaving out the condition and choosing to use the horizontal line?
No. Yeah. Actually, so you could have left off the horizontal line, and that would be fine too. And some people like to write their axioms that way, and that would be fine.
And so this would be
I would save a little ink.
Axioms.
What's that?
This would be in the category of axioms, or
I don't know.
like we would use this in the case that we were trying to describe an axiom.
Well,
Like,
I think it just doesn't matter.
Okay.
You could put the line there if you want to. I mean, it's basically saying true implies this other thing, and so.
Okay.
I think whether you have a line above it is probably like what's the best syntax for comments.
Yeah. I mean, it's kind of doesn't matter. Yeah. All right. Any more other questions about the horizontal lines? Yeah.
What about exists? Do you have to explicitly specify that?
Yeah. Yes. Yeah. Yeah. If you want to do anything else, I guess one other thing I left out is if you have multiple premises, it's sort of like implicit. There's sort of an and there. Whereas like up here, if I had multiple premises in English, I probably would have used the word and. But on down here, if you had multiple premises, there'd just be a space in between them, and that means and. If instead you need an or, you need to put an explicit or in there. Or you might just do 2 rules instead of 1 rule. Okay, so again, we've got our inc relation or function. And then let's say someone comes up to you and says, you know what, I think 2, 3 is in the relation. That's my claim. And you're like, I'm not sure I trust you. Prove it. All right. So what constitutes sort of a proof that 2, 3 really is in the relation? And the thing that you want is a derivation. Okay, and I've shown an example of a derivation down here with the multiple horizontal lines. And so a derivation is this sort of tree, sort of upside down tree. Well, no, yeah, it's a tree structure where every sort of node in the tree here, every horizontal line is, you're using one of the rules, okay? And then for the premises, you might, you're using maybe the same rule or a different rule, and you're chaining them all up together to arrive at the conclusion that you want, okay? So let's kind of work through this. That very first one, we're going to read it from top to bottom, right? So that first one, 0, 1, is in the relation by rule 1, right? And then this next one, we're going to say, okay, 1, 2 is in the relation by rule 2. Okay, so what's going on here? Look up at rule 2. We're saying, oh, put in 0 for n and 1 for m, right? Because that was for all quantified, so we can put whatever we want in there. 0, 1, and then below, we're going to get 1, 2, right? So that's good so far. And then we just sort of do the same thing again, but with different numbers. We apply the same rule, but with different things plugged in for n and m, and we get the conclusion 2, 3. So your friend hands you this derivation. You read through the whole thing, checking that the rule applications were all matched up properly to the real rules, and you're like, cool, awesome. I believe that 2, 3 is in the set. Okay. So derivation is an important word, and that thing down there is a particular derivation.
This doesn't scale though, right? So if I wanted to see if, I don't know, 99 and 105 were in the set, I don't want to do that many lines.
So oftentimes we don't have to do this stuff by hand, and then more often we're maybe just doing a proof that something is in a set, and then we can buy. So yeah, you typically never have to actually yourself by hand do a long chain of these things. So yeah, but you might very well write a computer program to do that. So for example, a type checker is actually something that you can think of as building a big derivation. At least sort of in your mind, it's doing that, even if it doesn't literally build the data structure to represent it. So. All right, I threatened that I would do some exercises. So we're going to do, let's do like a 5-minute break, okay? And we've got 3 tasks. The first one is to define the even natural numbers. So I wrote them out there with the ... dots, but your job is to write down some rules that define that infinite set. Then the next thing I want you to do is give a derivation that 4 is in the set of even numbers. And then maybe as a slightly more challenging task, define the set of all binary trees. Okay, so binary trees are, every node has 2 children, or at most 2 children. It could have 0 or 1 or 2. It should satisfy the max heap property, okay? I've got like priority queues on the brain, okay, because I teach data structures. And so a max heap, it just means that if you've got a parent and you're looking at its children, the key there, the number on the parent, is bigger than its children. But the ordering amongst the children doesn't matter, right? The siblings they're not ordered or anything. There's no relationship there, but just that the parents have to have numbers that are as big or equal to their children. Okay? And so you can use definition by rules to define that as well. And after the 5 minutes, I'm going to ask for some brave volunteers to share their solutions. Okay? And we'll write them on the board here. Is this a good time to continue on? All right, maybe can someone volunteer their definition for even? Some brave soul. All right. Maybe go ahead and just tell me your definition. Or maybe I'll look.
Base case for 0 in even.
Okay, very good. So we've got the base case with 0 in even, and then
An inductive case where above the line is n in even, and below n plus 2 in even.
very good. All right, so that's a perfectly good solution to that. Does anyone have a significantly different solution? Everyone? That was the one I was kind of hoping for people to come up with. Anyone go crazy and do a mutually inductive definition of evens and odd numbers together? That's a legit thing you can do, is define two sets at the same time with a batch of rules, and they can refer to each other. Were there any smart Alex that just wrote one rule that says n is even if n mod 2 equals 0? Here or? Oh, as an alternative.
No, you just say 2n is a member of even.
Yes. Yeah, right, okay, so there's one version, there's another version, and then, actually this is quite nice, 2n is in even. Yeah, there's another one. Right, so these two didn't even use the recursion, and so it's not even really inductively defined. I mean, in some sense, this inductive definition thing was overkill for even, okay? But it's a really nice, simple example, okay? All right, so great. Let's move on to the binary trees, okay? Fortunately, I'll need this space again. All right, do we have, oh, I'm sorry, I'm skipping ahead. 4 in even, someone else. Did someone else have a derivation? Hand up, or it's too obvious to say? Okay.
On top of rule 1, 0 is even.
Yep.
Below that, rule 2, 2 is even.
Yep. Yep. Right. So 0 is in even, and then 2 is in even, and then 4 is in even. Yep. Very good. Yep. That's exactly right. All right. Okay. Now on to binary trees. Someone have some rules they'd like to share? Yes.
So a leaf or otherwise the empty is in the set.
Okay. So you're saying. So your first one is a leaf is in the set. So I'm just going to sort of draw this as like a circle with a number in it is in this. Let's call this set the heap. Okay.
Okay. Well, the way I had it defined was that leaf is like it's one that doesn't have a number in it. It's the absent, because you said.
Okay. 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 Sorry, I misunderstood what you said. So some sort of like null.
Just a list, right? So like empty list or a singleton or a pair.
Yeah. So I'll just go ahead and be explicit and write null there, but that's fine. And so that's rule 1, okay? And by the way, there's different ways to do that. That you could do a leaf with something in it, or you could do null. That's either way is fine. Right? And then what was the next rule?
Singleton would also be there.
Okay, so you went ahead and had a singleton there as well. Okay. N is in this heap data structure. Okay. And then rule 3.
I think it would be the tree is in heap if both of its subtrees are also in heap.
Okay. So let's do this as a horizontal line, okay? And so and maybe I'll do pictures, okay? And down here we're going to have a conclusion that something is in the heap, right? And so what do you want me to put down here?
Okay, so what we're trying to prove is that n, or whatever our current tree is in the heap, and both of the below subtrees start with a number lower than n.
Okay, so we've got some subtrees here. I'm going to draw a subtree as like as a triangle, sort of with a circle on top. Okay, and so I've called that one n. I'll need to use different labels for this, maybe I and j. Okay. And then so now what do I need to write on top?
If I and j are less than n.
Right, so I less than n, j less than n. Okay? Or, sorry, less than or equal, right? Okay? What else? What's that? Okay, this is a good point. So if this rule won't apply to having nulls as children, okay? So yeah, so it might be that it's maybe less elegant to have to use the null case. But anyways, we're not done yet with this rule. What else do we need to say? So far we've said that this thing is a heap. This big giant tree is a heap if it's got two children who are less than, whose numbers are less than or equal to n. Okay. Yes.
The subtree I, the little current notation, is a heap of subtree j.
That's right. So we need to that these little subtrees better already be well-formed heaps. Okay, and so that recursion was absolutely necessary. Otherwise, this is just sort of saying maybe like at the root, at the very top, we've got the right structure, but then it could have been garbage underneath, right? So we have to sort of keep descending down recursively to make sure that the whole darn thing is properly structured. Okay. Yep.
If you have the condition that I is less than or equal to n, or I is null, then the same case you can get heaps where you have like windows where you have to the left on 5.
Yeah. So yeah, we're gonna. Right. So this one is sort of saying that you have to have both children. Then we'd need rules for like if you only have one child on one side or the other. So we'd need some more rules for that.
Yeah, that's where the null would come in.
Right.
If you define the empty child as a null child, then all trees inherently have two children.
Right.
The second one being implied null.
Right. Yep. Yep. So there's sort of different ways you can play around with exactly how you do that. But good. I think people have got the sort of the general idea of how these things work. I oftentimes think of these derivations that you get from these kind of things. I think of those actually as a very concrete data structure, actually. Even though, I would never have a computer program that, or very rarely would have a program that builds these things. I still think of them almost the same exact way. Okay, so with that, so now we've got our definition by rules. And then we're going to go on and start using it for some other things. But before that, there's another question.
We might be in the same case. What if there is a paradigm, but there is only one child?
Yes, that's right. I don't know if you just heard, but I mentioned that we'd need another, at least 2 more rules to cover those other cases. So you're absolutely right. Yes. Thank you. Yeah, it's always, you want to really be exhaustive, you know, and think through all the cases when you're doing this. Very good. Okay. All right, so let's talk about defining the syntax of a language. Okay. So what is a language? It's a set of programs, right? These programs are these textual things. In my mind, I think of them usually in terms of abstract syntax trees, if you know what that is. So I see the syntax, but then I really have a tree in my head. But if you don't know about that, that's okay. And so here we have this set of, this little language of arithmetic, right? We've got natural numbers, we've got, integers, plus, and minus, and negation, right? And again, I've got this horrible ellipses, this time going vertically down, right? So this is like completely not formal or precise, like what on earth is this language, right? This might be fine for some quick and dirty documentation for your users maybe, but certainly won't fly at POPL to define a language, okay? So how can we define this infinite set? Some rules. Yeah, let's write down some rules. This is not a relation, right? It's not a set of pairs. It's just a set of programs, right? We'll get to relations on programs in a moment. All right, let's write some rules. Okay. So we're going to say that a number, one of those integers, is in the language, right? So that's rule number one. That first rule. The second rule says that if you have some program E in the language, then you can put a negative sign in front of it. And notice that I've used sort of this dark negative TT font, typewriter font, means that this is a piece of syntax.
Okay, that's what I was worried about. When you say if E is a member of arithmetic, then minus E, like if 5 is a member of arith, what you mean is minus sign followed by 5.
That's right.
And not the number minus 5.
Right. Yes. Yeah. So I'm talking about like this kind of thing here where you've got a minus sign in front of something, right? So we're in syntax world here, and these things are these little trees, and there's a node with a minus sign on it, and that's what we're talking about. In a little bit, we'll have minus signs that are in a different font, and those are going to mean do the negation, okay? And I'll pause for a second when that happens. All right. Right, so we're not doing any work at this point. We're just defining, like we're not evaluating programs. We're just defining what these syntactic entities look like. If you have two little arithmetic programs, E1 and E2, then you can combine, then you can sort of stitch them together with a node, a plus node, with two subtrees. Yeah.
Sorry, I'm a little bit picky, but here we're trying to be like extremely strict, right? So how come sets get into this discourse? What kind of sets? I build in stuff on a certain set theory like Termelo-Frankel, or what is it like? How come E, whatever is a set? Like is an element of a set. So we're building a set. Why is it a set? Why are we talking about sets?
Yeah. I'm sorry. I'm not gonna go there. I'm sorry. There's a different.
We can just keep in mind that like there is a vagueness in that dimension.
Yes.
Aren't you just trying to define the property of the expression? So the set notation is the shorthand, but it's a property of the expression.
Yeah. I mean, I'm trying to. I mean, in some, or maybe I'm reading too much into your question, but I'm just trying to define this particular set here, this arith set. And I mean, are you worried about where the members of this set, like what the type is of those members? Or?
That one is totally perfect, but when you say like a set of programs, so.
By program, I literally mean just one of these things. That's all I mean, literally. I was just trying to, a lot of you are functional programmers, so I'm just trying to use terminology, but it's a little informal, so, yep. Yeah, so that's all I meant, is just that one of these little arith, if you've got these two members of arith, then you've got another thing in arith that has a plus in between, a plus symbol in between. And then, oh yeah, and then you can add parentheses wherever you want, right? So that's that last rule says if you've got something in arith, then you can put parentheses around it, okay? So that defines the syntax of the language. Okay, it's just good old definition by rules. All of what you know about definition by rules just comes over straight away and applies to this, okay? But, this talk is all about notation. So there's lots of other notations for this stuff. We're going to see 2 more notations for this. They're all going to mean the exact same thing. It's just different notation, same idea, okay? Backus-Naur form, okay? So this is a super common notation for defining the syntax of a programming language. And what's going on here, so each of these is a rule, each one of these : equals sign. And the left-hand side is sort of like saying, well, if it's in the right-hand side, then it's in the left-hand side. Okay, so if you're an integer, then you're in arith. If you put a negative sign and then an arithmetic thing, then you're in arith. Okay, so the premises are kind of on the right, and then on the left is the set that you're in. Okay, and then you can also use the bar means or. So if you want to, you can collapse multiple rules into one rule by using or, and that's a quite common thing to see. Usually in POPL papers, they're trying to get as much in one line as they can, so they use or to squish things down.
And so they're using, in this case, this to define the tokens and the way the tokens are arranged.
Yeah, so here, right, this is, BNF is really explicitly about strings of characters and not abstract syntax trees. But yeah, it's.
But I guess it implies that white space is significant or insignificant.
Yeah, and there's all these, but we're not gonna care about any of that. But you're right that there's sort of like these lower level details about exactly what this does. Like if you were to type it in like Yak and Lex and try to write a parser for your program, right? That's where these things are used quite a bit. But it's really, from sort of, if you sort of don't worry about that kind of thing, it's sort of the same idea going on. Okay. So that's BNF. So you'll probably see those quite a bit. Now I'd say that this gets used quite a bit in sort of like industrial defined languages and older languages. You don't see this notation used exactly like this in POPL very much, or the PL papers. Okay, instead there's this other notation which is more succinct, but in some sense is worse, because it's like there's all these puns going on. Okay, it's quite strange. Okay, so keep that BNF in mind. Okay, so we're saying the arith language has integers and negation and addition and parentheses. Okay, so what we're going to do is we're going to select some meta variable names that are going to be ranging over certain things that we're trying to define. Okay, so I might pick n and m to be placeholders for integers, and the variable e for arithmetic is going to range over arithmetic things. And now I'm going to do this weird pun thing where I replace in the grammar everywhere that I would have written arith, instead I'm just going to write e. And everywhere that I would have written integer or z, I'm just going to put an n there. Okay, and now we get this super concise little grammar rule. Okay. So that's what that's all about. And it's kind of a weird pun thing going on, but it is what it is.
You might have said this, but what is POPL?
Oh, that's the Symposium on the Principles of Programming Languages. It's one of the really good conferences on programming language theory. Yeah, and I'll actually have a link or an explicit sort of pointer to it at the end of the slides, and it'll be there for you to follow up on.
Why do they still teach BNF in a lot of undergraduate schools?
Well, I mean, BNF's better, right? It's well.
I mean, because then when you want to go to, if you want to do PL,
Right.
you have to rewrite.
Yeah. Well, so the BNF, I mean, like I said, if you want to write a parser and like use Lex and Yak, then you definitely want to be knowing all about BNF to do that. So like in my compiler course, I teach, BNF. And it's, I mean, the world of programming language theory is actually a very small microcosm within the bigger world. And so, and I think there's probably, if you look at the whole world, there's probably more people using BNF, right, than this funny PL theory notation. Okay, but you're right. I mean, if what you do want to do is PL theory, then you need this notation for sure.
About the parentheses, I looked at papers and they had parentheses, and I was like, what do parentheses mean in this paper?
Right.
Do they usually just mean, I don't know, precedence or something? What do they mean?
Okay, so
If you can have them, but they don't define them, or
right. So here you'll notice I did not mention parentheses, right? And no one ever puts parentheses in, but then you look at their examples and there'll be parentheses all over the place.
Right.
Okay, so they're just implicit that yes, you can always, no matter what language you're defining, doesn't matter what language, it's got parentheses. The whole community has just agreed that you've got parentheses, and oftentimes we do use them because we don't want to think about precedence, and
that's what they mean is precedence.
Yeah,
basically.
yeah.
Have you seen Guy Steele's talk he gave at the Closure Conf?
Not that one. No, I've seen a lot of other of his. I know he's been talking about notation and making fun of like substitution.
I'll send you a link.
Yeah. So I keep hearing good things about that. So check it out. Yeah. Was there another hand? Okay. We're now time for another exercise. Okay, so what we're going to do is we're going to grow this language. Okay, so we have this arith language. We're going to add in pairs. Okay, and what I mean by that is you need to be able to use the parentheses and comma, to form a pair. And you also have the subscripting to extract the first or second, element out of a pair. Okay, so I want you to sort of extend the grammar or for arith to also have what you need for pairs, for forming pairs and selecting, the two items out of the pair. And here's two example programs. Okay, this program on the left is pretty simple. The program on the right is a little more hairy, and hopefully the grammar that you write down, or in whatever form, the definition by rules, however you want to do it, hopefully those two programs fit and are in the set that you defined. Okay? So let's take a few minutes for that. And would you like me to write down the grammar for arith, for just good old arith here as reference? I'll do that up here. It's kind of so you can know how to get started. Oh, notice also that in the PL sort of theory notation, we dropped the quotation marks around the literals, the string literals, or the terminals, you might say. All right, so back to that.
How should we try to make the type check though, like statically typed?
Don't worry about that. That'll come later with the type system.
Subscripting is like first and second in pair.
Yeah, or 0 and 1. Yeah.
Can we allow sort of bad programs in the sense like 2 subscripted with 0, even though it's not a pair?
Yeah, you can allow that. Yeah. We'll get into that kind of restriction later on. So yeah, it just has to sort of like yeah. Don't worry about the types. Is maybe one way to put it. So I guess what was the what was just asked is, is this a valid program syntactically? Like the number 4 subscripted with 0, and I'm saying yes, that's a perfectly fine syntactic program thing. That's going to be that this indeed we want this to be in arith pair. And you might be like, oh, this thing is nonsense, and you're right, it's nonsense. But the job of saying that this thing is nonsense is going to be not the problem of the grammar that we're writing down. It's going to be the type system, which we'll get to in a minute.
You also have a pair that is not subscripted. There's one pair that is not subscripted.
That's okay.
So
Yep.
both are-
You don't have to have pairs. Don't have to be subscripted right away. Yep. That's a good observation.
Are we only allowing for pairs?
No, I mean, we got numbers, we got addition, we got subtract, negation there. So it's all the arithmetic and pairs. Yep. And they can be sort of arbitrarily nested inside of each other. Great. These are great questions. I think we're kind of getting into some of the maybe slightly trickier ways of thinking about these things.